Up till now, we've considered dissolving weak acids and bases in pure water. We might also consider what happens when we dissolve them in solutions that are already acidic or already basic or contain some ion or something like that. We're led to consider something called the common ion effect. Most textbook authors reserve that term for studying solubility problems, but they come into play here with acids and bases also, and we'll see that. But it leads us also, and perhaps even more importantly, to consideration of buffers. Buffers are very important in a lot of experiments. There are solutions that hold the pH constant, and we need to learn how they work. But let's consider first what happens if we dissolve a weak acid in a solution that's already acidic. So here's some benzoic acid, okay? Got tired of acetic acid, so it's benzoic acid, okay? But it's doing the same thing, dissolving a little bit. It's a weak acid, making H3O+, and its conjugate base is benzoate. C6H5COO- is benzoate, okay? Here's what the compound looks like. It's just a benzene ring with a carboxylic acid group on it. Its Ka is 6.5 times 10 to the minus 5, sort of run-of-the-mill Ka for weak acid. And suppose we had a 0.1 molar solution of it. If we did that just dissolving it in pure water, we can do that calculation very quickly now, right? A 0.1 molar solution, multiply 0.1 times Ka, take the square root. That would be the H3O+ ion concentration as well as the benzoate ion concentration. The X is small approximation is embedded in that calculation. You have to check it and so on and so forth. But we've done this many times. So here it is. 0.1 molar solution gives you 2.5 times 10 to the minus 3 molar in H3O+ and benzoate. And the pH of that solution would be 2.59. Okay. What I'm interested in here, though, a little bit is the percent dissociation. If the concentration of benzoate is 2.5 times 10 to the minus 3, and the original total amount was 0.1, the percent dissociation is the ratio of those two multiplied by 100, and that turns out to be just 2.5% dissociated. Only 2.5% of the benzoic acid actually turns into benzoate. Here's the ice table that you would use to do that calculation. We've seen it many times, but I want to compare it in this next example to other situations. Let's consider the same thing, only this time, instead of just dissolving it in water, let's dissolve in a solution that's already acidic because it's a HCl solution, all right? Dissolving 1 molar solution, making a 0.1 molar solution of benzoic acid, but this time not in pure water, but in 0.05 molar HCl. Now, HCl is a strong acid, so that means you have 0.05 molar H3O+ to start with, okay? And also Cl-, but the Cl- doesn't do anything. Now, how does that ice table look? Instead of the ice table's top line with the initial concentrations of H3O+ being 0, as in the previous example, here the H3O+ concentration is initially 0.05. That 0.05 molar H3O+ is from the acid, the HCl. Now the benzoic acid attempts to dissociate just as it did before. X representing the amount of benzoate that's formed, and also the amount of additional H3O+ that's formed. So at equilibrium, it's 0.1 minus X for the benzoic acid, and 0.05 plus X for the H3O+, because it started out at 0.05 and we added X to it. And the benzoate is just X. And as we always do, we put that into our equilibrium expression. And you're probably expecting something rather messy algebraically, but in fact, it's simpler than problems we've done before. Let's again look at our x is small approximation as a possibility here. It's a weak acid, doesn't dissociate much. Perhaps x is small compared to 0.1, and perhaps x is also small compared to 0.05 in the numerator. In other words, maybe we should at least check and see, is it possible that 0.05 plus x can be just approximated as 0.05, and 0.1 minus x could then be approximated as just 0.1. If so, that leads to a very simple equation that the Ka, 6.5 times 10 to the minus 5, is just equal to 0.5x, which means that x is 1.3 times 10 to the minus 4. Okay, so is our x a small approximation looking good here? 10 to the minus 1.3 times 10 to the minus 4 would be 0.00013. Okay, and we would be adding that to 0.05. So I think that that's a very small addition to our 0.05. So our x small approximation should work. Let's check anyway, the way we usually do. Now, you might be used to just looking at that denominator. We neglected x relative to 0.1. An even more stringent test, is it okay to neglect it in the numerator compared to 0.05? Okay, so that's what we've checked here, right? It would have to pass both those tests, and clearly if it passes the one we're doing here, it will also pass the other. So it comes out to be a very small fraction, 0.26%. So no problem with our x is small approximation. And what does that mean for all the concentrations that we have here? Well, the benzoate is 1.3 times 10 to the minus 4, that's x. The benzoic acid is essentially unchanged. 0.1 minus x is essentially 0.1. Look at the hydronium ion, the H3O plus. Now it was 0.05 because of the HCl that we started with, and now we've added a tiny amount to that. It's still 0.05, okay? And that 0.05 is coming from the HCl, really, most of it, nearly all of it, okay? And the pH, for the pH, you might be used to just taking the value of x and sticking it in there, but here now, the pH, the H3O plus is, again, it's from the HCl. It's the 0.05 from the HCl that dominates, and the pH of this solution would be 1.3, the negative log of 0.05. Let's calculate again percent dissociation. You remember on the previous one where we were dissolving in pure water, it was 2.5% dissociated. Now what are we expecting? Would we expect more or less? You have to think back on Le Chatelier. Look at this equation at the top. If you put more H3O plus, which direction is this reaction going to shift? It'll shift to the left, right? It'll make more undissociated acid, okay? So according to Le Chatelier, we would think that the benzoic acid dissociates much less in HCl than it did in pure water, okay? And indeed, when we run the numbers, we find that out exactly, because the amount that dissociated is X, the amount of benzoate, divided by the original amount of benzoic acid. And it's just 0.13%. Before it was 2.5. Dissolving in pure water, 2.5% dissociated. Now only 0.13 dissolves. This is an example also not only of Le Chatelier proven correct, right? It's also often called a common ion effect, because the HCl dissociating in water produces H3O plus, and the benzoic acid dissociating in water produces H3O plus. So they have a common ion. They're both trying to produce H3O plus. The HCl is a strong acid, produces this H3O plus, and it inhibits the dissociation of the benzoic acid. The benzoic acid is much less dissociated in 0.05 molar HCl than it is in pure water. I mean, 2.5% in pure water, 0.13% here. That's a factor of roughly 20, right? So that's a significant effect. Okay. Now, we could do the same calculation very quickly. Suppose we increase the amount of acid that we have originally. Suppose we double it and we make it 0.1. Okay. There. Right? The same slide, different numbers. Okay. So now I've got 0.1 molar HCl. Ice table updated 0.1 instead of 0.05. We can go through this very quickly. Look at this equation now. Ka is equal to x times 0.1 plus x over 0.1 minus x. If we do the x is small approximation, and if it worked before, it should definitely work now because we have even more acid. Le Chatelier says it's going to dissociate even less. We're expecting x to be even smaller this time, right? But if we neglect x in the numerator and the denominator, 0.1 plus x and 0.1 minus x, we wind up with just x times 0.1 over 0.1, or just x. So it's very simple math this time. X is simply equal to 6.5 times 10 to the minus 5. Okay, so indeed x is smaller than last time. Last time it was something times 10 to the minus 4. Now we're inhibiting that dissociation even more. We can do the x is small approximation. It's great by a long shot. Let's look at the concentrations. The benzoate is 6.5 times 10 to the minus 5, x. The benzoic acid is 0.1, essentially what it started. Really 0.1 minus 6.5 times 10 to the minus 5, which is 0.1. Okay. H3O plus, again, that's 0.1. It's 0.1 from the acid, HCl, not from the benzoic acid. Added a teeny tiny amount to that, but it's 0.1. And then the pH is simply 1. Percent dissociation, now even smaller. Before it was 0.13%. Now it's 0.065%. Tiny. So the more acid we put on, the more H3O plus that we put on the product side from some other source, the less the benzoic acid is able to dissociate. It's a very pronounced effect. Okay. Well, another interesting problem that's very much related is, suppose instead of trying to dissolve benzoic acid in a solution that already has H3O plus in it, suppose we dissolve benzoic acid in a solution that already has sodium benzoate in it. In other words, you've got extra benzoate floating around instead of extra H3O in the initial solution. Okay, the math is very, very similar. Let's have a look. Here it is. Consider a solution of 0.1 molar benzoic acid dissolving now in 0.1 molar sodium benzoate, okay, which is the conjugate base of benzoic acid. The ice table, well, it looks like I just switched two columns, doesn't it? Before it was 0.1 under the H3O plus, now it's 0.1 underneath the benzoate. Okay, the math is identical. You're going to get an equation that looks like this, right? Because the numerator is just the two products multiplied together, and they've simply switched. And again, we have x is equal to 6.5 times 10 to the minus 5. And this time, though, well, of course, we can do our x is small approximation. There it is, same as it was before. It's fine. The concentrations, okay? Now, benzoate, we started with 0.1 molar benzoate from the sodium benzoate. At equilibrium, then, we've added x to that, but x is ridiculously small. So 0.1 molar is the concentration of the benzoate. The benzoic acid, we started with 0.1, a little bit of it dissociated, not enough to matter. It's still 0.1. It's 0.1 minus x, but x is very, very small. Now here, H3O plus, this time the H3O plus is coming from the benzoic acid, right? There's no HCl that we started with. Now it's just the amount that came from the dissociation of benzoic acid. It's very small. 6.5 times 10 to the minus 5. You take the pH, negative log of that, it's 4.19. Okay. So we can figure out problems like this, and the math is actually, I think, a little less complicated. You don't run into quadratics and things like that because, especially when you can neglect the x in the numerator and the denominator. But the more important thing, this is a buffer. You know, we're going to investigate the properties of buffers a little bit more, but this solution that we just made with some benzoic acid and sodium benzoate, that's a buffer. Anytime you have a solution containing significant amounts of both members of a conjugate acid-base pair, you have a buffer solution, okay? So here with the benzoic acid and sodium benzoate, and what these things are good for, buffers, is they resist pH change. Okay, once you have a solution like this, say it's 0.1 molar in benzoic acid and 0.1 molar in sodium benzoate, you have both those present. When you add acid to it, it simply converts a little benzoate to benzoic acid, and when you add base to it, it converts a little benzoic acid to benzoate. It swaps them back and forth, but the pH, we'll find, stays reasonably constant and resists changes, and it makes it very useful in a lot of experiments. So we'll investigate that further in subsequent videos.